What is the derivative of x to the power e plus pi to the power 3? So we have some options here. X to the e, ex to the e, ex to the e minus 1, x to the e plus 3 pi squared, or ex to the e minus 1 plus 3 pi squared. Do we have an answer? Anyone is like, I think I see the answer.
Is it D? C?
D, I hear C. B. C. D. The answer is C. All right. So, what's going on? Well, what are we taking the derivative with respect to? And the answer is we're taking with respect to x. That's what this notation means. The derivative with respect to x. What is pi cubed with respect to x? Well, pi cubed with respect to x is pi cubed. It's a constant. And the derivative of a constant is 0. You're like, oh. So you don't just bring down the rule. You know, you're like, shouldn't you have written as 3 pi squared? Well, that's a great story. We'll pick that up later in the week. But for now, it's just a funny looking constant. And then you say, well, wait a second. I thought the derivative of e to the x was e to the x. And you're right. But do we have e to the x? No. We have x to the e. And so you apply the rule. Ex to the e minus 1. Now, you might have looked at this problem. Maybe you got the right answer. Maybe you got the right answer, wrong answer, right answer. And you said, this problem seems too easy. Sometimes problems are easy. I've looked at the multiple choice problems that they selected for the upcoming exam. And I said, a lot of these are really easy. Not all of them. So don't overthink it. Don't overthink it. So, I see a question.
What would it be if it was e to the x? Would we just leave it alone then? Or
the derivative of e to the x is e to the x.
So we just leave it alone?
Leave it alone. The derivative is not able to do much with e to the x. Now, one other piece of advice, which is, I haven't thought of a good way to phrase this, which is when it comes to applying the rules. All right. What is he going to say? He's thinking of something. So when it comes to applying derivative rules, do not be creative. Be mechanical. Just be a machine. Don't be like, normally the derivative of pi cubed would be 0, but I'm going to have some flair today. Make it 17. No. Don't be creative. Write down the rules and just apply them exactly as. Now you might say, that doesn't sound very fun. Well, no, but you get the points. And we like the points. We want all the points. So just know the rules and get to the point where you can apply them automatically. It should be very minimal thoughts. Like, okay, I see derivative of x to a power. That I don't really care what that power is. I know the rule that I need to use is this rule, and I go for it. And I just run through the machine. Now, you might say, Steve says math has no creative aspects. Well, there are places where you should and can be creative. And oftentimes, the creative part comes in the setup and saying, okay, how do I think of this problem? How do I write this function in the best way? And in particular, once you start transitioning into the end of this semester and into next semester, a lot of the creativity is not in the rules and applying the rules. It's in getting to the point where we can apply the rules. So this is not to say, don't worry, I'm not saying you'll never be creative in math. I'm just saying, don't be creative when applying the rules. All right. Cool. So, if you've been following our thoughts for the day, we've been talking about problem solving. And that brings us to our final step. And let's recap. What was step 1 to problem solving? Step 1, we first need to understand. You can't solve a problem if you don't understand it. The second step was make a plan. All right, you should think about what are you going to do. And in fact, the second step ties into what we're going to talk about with the fourth step. How do you make a plan? Well, we have some good news. We're not very creative. The problems that we ask you to solve will be similar to problems that you've solved in the past. And so if you are able to understand what you've done before, it'll be easier to make a plan. Okay, so we've understood, we made a plan, and then step 3, do it. Okay, all right. Hopefully that's no trademark infringement. We'll say carry out the plan. All right, so we solve it. And you might say, well, you're done. You've solved the problem after step 3. So why is there a step 4, and why is it called look back? So after you solve the problem, you don't just say, all right, that's it, and move on with your life. Take a moment and look at the problem and say, what did I do? Why did I do that? Why did I do option A and not option B? What happened in this problem that was different, that was surprising? What did I do that in the future would help me to solve similar problems? Because your goal is not to solve one problem. Your goal is to solve all the problems that you're going to encounter that are similar in the future. So by taking some time to understand what you did and sort of synthesizing, if you will, what was the process? What were the ideas? That will help cement it. And it'll make your future problems easier. So that's why you should think about what you're doing. Don't just, for lack of a better words, be mechanical. Think about things. Think about things. All right. So there we go. Now we're ready, right? We can solve all the problems. Okay. So last time was a very busy day. And I feel like we need some more practice. And so if you remember last time we talked about rules for derivatives. So I was looking at some old exams. And I thought this one looks fun. So this is from an exam several years ago, back when they let me write exam problems. I don't know if I wrote this one, but whoever wrote it, it's a nice problem. And it says, we're going to tell you some things. We're going to tell you that y, which is 2x plus 1, is tangent to y equals f of x at x equals 1. And that y is minus 4x plus 3 is tangent to y equals g of x at x equals 1. That's what we're going to tell you. And then we're going to ask, find the tangent line to y equals f of x over g of x at x equals 1. Okay. Now, do we know what f is? No. We don't know. We know a bit about f, just a small piece. Similar, we don't know what g is. So we definitely don't know what f over g is, but somehow we have to figure out a tangent line. All right, now the good news is, if they ask, that means we must be able to answer. Okay, so let's start by figuring out what it is that they gave us and how that can help us. Okay, so y equals 2x plus 1 is tangent to y equals f of x at x equals 1. When I have a tangent line, it's telling me two things about the function. So let's say I have a tangent line at a point. For simplicity, since it's in our problem, let's suppose our tangent line occurs at x equals 1. That tangent line at 1 tells me two pieces of information about the function. What two pieces of information do I know? How do I get that information from the line?
The slope of your instantaneous rate
Okay, so someone mentioned slope, instantaneous rate of change. Okay, good. Tangent line, we talked about instantaneous rate of change as the slope of the line. In terms of the function, what do we call the instantaneous rate of change? The derivative. So one thing that we can recover for f is that f prime of 1, that's the instantaneous rate of change of the function at 1. That has to match the slope of the tangent line, which is a rate of change. Slopes are rates of change. So what is f prime of 1? We look at our line, 2. Slope. There is one other thing that we get. The word tangent means touch. What does that mean in terms of the function? It's a point. It touches the function at the point of tangency. I mean, that's, in other words, it touches the function at the point of touching. Is how that sentence would translate if we mean what tangency means. So, if we have that information, what is that telling us about the function? I claim it's telling us f of 1. It has to touch the function at 1. How do we get that value? Is it this number 1? And why not? Okay, it's not 1. How do you get it? Plug in 1. So the line has to match the function at 1. So plug in 1 into the line. What's coming out? 3. Okay. So every tangent line stores that two pieces of information. The value of the function at the point of tangency, the instantaneous rate of change at the point of tangency. And if I know those two pieces of information, I can get the line. So in essence, there's sort of this back and forth. Now, I think we can probably do it for the next line even faster because we're becoming pros at this. All right, so let's suppose we say, what can we say about G? What's some information we know? Do we know what G of 1 is? Negative 1. How do we get negative 1? Plug in 1. Do we know what G prime of 1 is? Negative 4. How do we get that? Well, yeah, we can take the derivative, or we just read off the slope. All right? So far, so good? Yeah. We're like, yeah. Okay. Good. So, when we're given information about tangent lines, we translate that. Now we're saying, okay, so secretly, when they gave us this, it was just a shorthand way of saying that. Now we say, okay, we're after the tangent line to this function. So let's, for a second, we'll call h of x, this f of x over g of x. Now, if we want the tangent line, what two pieces of information do we need to know about this function called h? So for the tangent line gave us information, but what else can we say? The tangent line needs this information. So, what do we need to find? We do need to find the derivative, but what do we do once we found the derivative? Plug in the point. We need h prime of 1, and what else do we need? We need h of 1. If we have those two pieces of information, we can make that line. Which one do you want to try to figure out first? H of 1 or h prime of 1?
Where are you getting the ones from? I think you might have done it the way it's done right over my mouth.
So the ones are coming from, we're at x equals 1.
So is that what's the negative 4 you're just talking about? Like what x is it bringing? Negative 4 is like a slope.
So this negative 4, that's a rate of change, because the derivative means rate of change, instantaneous rate of change. In terms of the tangent line, it matches the slope of the tangent line. So the slope of the tangent line gives us the instantaneous rate of change.
And negative 1 comes from like when you plug in that
Yeah. All right, I claim one of these is easier than the other. Yes, h of 1 sounds easier to do. So let's do that one first. Okay, so h of 1 is f of 1 over g of 1. What's f of 1? 3, because we said it was. What's g of 1? Negative 1. That gives us negative 3. Okay, so h of 1 is negative 3. All right. Now, what comes next? H prime of 1. Now, where do we plug 1 in? Well, we plug 1 into the derivative. Where's the derivative? Oh, we haven't found it. So I guess we better find it. All right. So h prime of x. That means we're taking the derivative of h of x. That's what h prime means. So you took the derivative of that. But the derivative of h of x is the derivative of f of x over g of x. Okay, so how do you find the derivative of f of x over g of x? Quotient rule. So it's one of those rules that we just have. It's at our disposal. So we're going to take low d high, so I'll write it as f prime g, minus high d low, f g prime, all over low squared. So that's oftentimes how I write that. Of course, we probably should put the of x's in. So f prime of x, g of x minus f of x, g prime of x over g of x squared. Okay. And the hardest part about, the quotient rule is probably the hardest rule to remember, because which one comes first? And so whatever you do that makes you remember it. If it works, it's great. Okay, so now what can we do? We're getting close. The end is in sight. The end is near. What comes next? Yeah, plug in, right? So we have that h prime of 1 is f prime of 1 g of 1 minus f of 1 g prime of 1. So this problem, it's testing our knowledge of the rules, and downstairs g of 1 squared, but it's also testing our knowledge of what tangent lines are. And tangent lines are important. Okay, so now we have a bunch of values. Do we know anything about these numbers? Yes, we know a lot of things about these numbers, like these numbers are these numbers. So we just do a matching thing. You say, okay, f prime of 1, well, that's the number 2. G of 1, well, that's the number negative 1. Subtract. F of 1 is the number 3. G prime of 1 is the number negative 4. G of 1 is negative 1, and we're squaring that. Well, it turns out negative 1 squared is 1, so we don't need to worry about the denominator anymore. And let's see, what do we have? We have minus 2, and then we have plus 12, also known as 10. So, h prime of 1 is 10. Are we done? No. There's a suspicious amount. No, it's not because there's space left on the page. It's, what did the problem ask us to find? Tangent line. So we're not done until we've given them a tangent line. So, what's the tangent line? Well, y minus what?
Wait, wouldn't the 12 be negative?
Well, there's a minus and a minus. So y minus, what goes here, equals something, x minus, what goes in these slots?
Isn't it
y minus your y minus your y value is equal to your slope, 10, x minus your x value. So this is your y value. This is your derivative. In this case, it's h, not f. And this is your x, your f of x0. Now, that's it. You can leave your answer like that. If you want, you can rearrange this. This says y equals 10x. You have a minus 10. This is plus 3. Bring it over to be a minus 13. And that's fine. This is also fine. And there we go. Boom! 10 points. On our way to that A. Straight ahead. Second star to the right. Straight on to morning. Or the second star to the left. I can't remember. One of those two. Okay. All right. Any questions?
Does it matter which order the f of x and g of x go from when you're subtracting the equation?
Well, yes. Yeah, you have to be very careful. You have to make sure you get the rule. So it's the bottom times the root of the top minus the top times the root of the bottom. You have to be in that. If you get it backwards, what will happen is you'll lose a sign, a minus sign. Usually, if it's not multiple choice, that's a point. If it is multiple choice, that's everything. Live by the multiple choice, you die by the multiple choice.
So then, how do we know which one goes in front? Will it just be, just assume that f, if it's like f and g, would it just be just throw f in the front?
Well, you know the rule. And I know that's not very comforting to you. But you know which one goes where because you have the rule memorized. And you just apply it automatically.
So those would be labeled f and g of x.
Well, you have something that's on the top and you have something that's on the bottom. And so you say, okay, it's in this case, but it's just, you have to understand what's on top versus what's on the bottom and where does it fit in over here.
Okay, that's what I was thinking.
It's,
of letters. I didn't think of the function.
I mean, oftentimes I've heard it as low D high minus high D low. Is that not it? Yeah, low D high minus high D low. That's the phrase I've heard for what goes upstairs. Let's see. All right. So.
Okay. No, I see where I'm wrong. Because if it was G over F, it would be the other way around then.
Right, yeah. You just have to keep track of what's on the top, what's on the bottom. Okay, so there's our review. And now, in our remaining time, we have today. Okay, so higher order derivatives. So we've talked about a derivative. We have this notion of derivative. We say, look, we can take a derivative, no problem, no problem. We have this idea, y prime, f prime, dy dx. But we can also talk about second derivatives. Now, what does that mean? Well, not surprising, the idea is to say, well, I have this machinery called derivative, and I plug in f of x, out comes f prime of x. The second derivative says, hey, throw it back into the machine. And we'll have it do it again. So if I plug f prime of x, the second derivative is denoted f double prime of x. So it's you're applying the rules multiple times. And when I say the rules, the derivative rules. So that's what we mean when we talk about higher order derivatives. It's just you keep taking derivatives multiple times. You keep feeding it into the machine. So notationally, this y double prime is d squared y dx squared. But it's the same as the derivative of the derivative. That's what we mean. Which you can write as the derivative of y. So it's like we're taking the function y and plugging it in through this operation and taking multiple derivatives. Now we can keep going. We can talk about third derivatives and fourth derivatives. So in general, if we have the nth derivative, we can say, well, the nth derivative of y, we'll use this notation where you have this y, and then you have this sort of upstairs n, but it's in parentheses, or f, upstairs n in parentheses. If you see that, that's a shorthand way of saying I'm taking a high order derivative. Now you might say, well, why do that? Well, you might think, for instance, suppose I want to take the 17th derivative. Okay. Versus the 17th derivative. After a while, which one do you think is more convenient to work with? Once you start getting to higher order derivatives, it's much easier to use this notation. So then you don't have to start counting the number of primes. And usually sometime around the second or third derivative, we say, okay, let's just use this other notation. I hope there's actually 17 there, I think. All right. So higher order derivatives is nothing more fancy than saying, oh, you just take some more derivatives. Just keep plugging it through the machinery. Keep plugging it through the machinery. So, okay, all right. One thing we should talk about well, let's come back to let's try this example. Here's a function. G of x is 2e to the power x plus x to the power 8. And it says here we want to take some derivatives. We want to take the 10th derivative of the function evaluated at 0 for this function, 2e to the x plus x to the 8th. Then we'll take the 100th derivative evaluated at 0. And then, just for fun, we'll try the 8th derivative evaluated at 0. Okay, so let's think about what's happening. So g of x is 2e to the x plus x to the 8th. What's going to happen when I take a derivative? What does it look like? Well, you have two things being added, so you can take the derivative separately. What's the derivative of 2e to the x? 2e to the x. What's the derivative of x to the power 8? 8x to the power 7. The power goes down. How about g double prime of x? 2e to the x. What about this next part? It's 8 times 7, x to the power 6. How about g triple prime? Now, our goal is not to write down 100 derivatives. Our goal is to say, can we start spotting some patterns? 8 times 7 times 6, x to the 5th. So what's going to happen is we're going to keep bringing powers down. Can we spot any patterns happening here? There's a couple of patterns.
Wait, do you eventually start multiplying by negative once you go count that?
Well, okay, you're getting to the hard part. Let's start with the easy part. What do you notice about this? Yeah, it's very consistent. E to the x, just e to the x. It's very nice. Now, if there was something attached to it, it'd be a different story. But I say, okay, so we understand what the pattern there. Now, people are saying, okay, but what about this part over here? Now, let's talk about the powers of x. What's happening to the powers of x? The powers that be, if you will. They're going down, right? What's going to be an interesting power for us? And when will that happen?
0.
An interesting power might be 0. When would we get x to the 0? What derivative? We have that 2e to the x. We'll have 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1 times x to the 0. X to the 0 is also known as 1. What derivative does that happen? The 8th derivative. Because every derivative, the power goes down by 1. So if I want to start up the 8th power, x to the 8, I want to get to a power x to 0, I had to have gone 8 steps. When we take this next derivative, what happens? Well, the 2e to the x is 2e to the x. And then this part is 0. So we're not going to get negative powers because we get down to x is 0, which is 1, which is a constant. Okay, so what's the 10th derivative? Yeah, 2e to the x. What's the 100th derivative? Yeah, 2e to the x. So this is about patterns, spot patterns. So we can answer questions. What is G10? The 10th derivative evaluated at 0? 2. G100 evaluated at 0? The 100th derivative evaluated at 0? 2. The 8th derivative evaluated at 0? 40,322. Right? Because we all know 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1 is 40,320. But don't forget you have to add 2.
Where did the e to the x go? For the if we put x equals 0.
Well,
0, would that just be 1? Oh. No, it would just be e.
Well, e to the 1 is e. E to the 0 is 1. So, by the way, you don't need to know that 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1 is 40,320. It's just one of those random conversation starters. You know, you're standing in line. Hey, do you know what 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1 is? No. Do you? Yes, I do. All right. So learn to spot patterns. If you have higher order derivatives, the way that you do a higher order derivative is you don't sit down and be like, let me do 100 derivatives. You start saying, let me do like 5 or 6 derivatives and be like, there's patterns. Lots of patterns. We'll see this especially, I think, next time's lecture. We're going to see these patterns be like, oh, these patterns are beautiful patterns. They're the best patterns. And so they're going to save us a lot of work. All right. So a quick conversation. I want to talk about units of derivatives. And I'm not necessarily a huge fan of units. I tend to avoid them. My rule of thumb is that units work themselves out. What you need to be true is what will be true. It's okay, all right, great. Life is good. But where do they come from? And so if you think about the definition of the derivative is this limit as z goes to x. You have f of z minus f of x over z minus x. And so in particular, this f of z minus f of x, this part upstairs, is a change in y. And so it's the units of y upstairs. The downstairs is z minus x. This is a change in your input. So it's a change in x. So it's the units of x. So if you have a function, and we'll talk about things, but you can make up anything. So like s of t, what's something you might want to measure? We can make up a word. We could say the number of tribbles. They can cause troubles. You can get a lot of troubles with tribbles. Okay, so s of t is the number of tribbles, where t is the number of hours, since you've docked at the space station. What would the units of s prime be? Tribbles, the output per hour, the input. How many tribbles are being generated in a given hour? The rate at which tribbles are generating. All right. Now that's the first derivative. What about the second derivative? So the second derivative, well, that's the derivative of the first derivative, right? And you can even go through it. We won't do it, keep going, but do it again and again and again. But it's f prime of z minus f prime of x over z minus x. And so upstairs you have your units of the derivative, and downstairs it's your units of x. But you know your units of your derivative because that's what we just did. So you say, ah, that tells us something. This is our units of y over your units of x squared. So, going back to our triples, what are our units of our second derivative? It's triples per hour squared. And I might want to say, well, wait, what is a square hour? What does that even mean? Well, it's not triples per hour squared. It's actually triples per hour per hour. But instead of saying triples per hour, we just say triples per hour squared.
Isn't that acceleration?
It is acceleration. Yes, it's how fast the triples are accelerating. And they do grow quickly. That's why they're troublesome. Triples are trouble. Until you run out of grain. So, but anyways, that's a different story. All right, in general, the nth derivative, if I want the units, what will they look like? Upstairs we'll have the units of y. Downstairs, units of x to the nth power. And I actually like this notation because you'll see, say, oh yeah, I only see a single y here, then I see x to the power n downstairs. So it matches what you see, what you would expect to see. All right. So I will say it's not just usually triples, it can be anything. So one of the things that derivatives get constantly used for, this shows up a lot in physics, are talking about things like rate of change. So you have things like position, you're like keeping track of position and how things change. Particle motion. So you maybe have a small particle and you're saying, well, where's that particle? Now, because this is our class, we're just beginning, we can think of it as there's this line, and then we have this particle that can move back and forth. So maybe it moves to the left, maybe it moves to the right, just depends. But S of t is the position of the particle at time t. So we have things we might want to know. We might want to know, well, what's the velocity? Well, what is the velocity? You can read it there. It's change in position, how your position changes. Once you hear the word change, what should pop into your head? Derivative. Derivatives are about change. So if velocity is how position changes, then what should we do to get the velocity? We should take the derivative of position. So the derivative of position is velocity. Now, suppose you say take the absolute value of velocity. What is that? And why is it different? It has a name. It's speed. What's the difference between velocity and speed? Velocity includes direction. I might say, well, wait, it's just a number, at least for our class. How could a number include direction? Well, it turns out that there's these things called plus and minus. So when your velocity has a plus sign, this is to the right. When your velocity has a minus sign, this is to the left. So velocity is encoding some direction information. And here it's just very simplistic left or right. Now, if I don't want to be moving left and I don't want to be moving right, what should my velocity be? 0. So stationary means velocity of 0. All right, acceleration. So acceleration is saying, how does your velocity change? Well, if I want to know how my velocity changes, what should I do? Take a derivative. So change means derivative. So the change in velocity is v prime of t. Is there another way we can write that? S double prime. So the second derivative of position is acceleration. All right. Cool. Cool, cool, cool. Let's see. Is there anything else? I felt like I had some notes I wanted to do here. Okay. So we just do a quick example. So suppose we have a position. Let's say it's 10t squared plus t e to the t. And where meters at time t, which is in minutes. Oops, I can spell minutes. Promise I'm trying to read and spell at the same time. So there's our position function. What would be our velocity function? (20t), derivative of 10t squared is 20t. How do you take the derivative of t times e to the t? What rule do you need? Product rule. How do you know you need the product rule? Because there's a product, right? There's multiplication. Okay, so product rule, everybody gets a turn. Let's start with this one. What's the derivative of t? 1. So we'll have 1 times e to the t. And then, now, so the derivative of the first times the second, plus the first, t, times the derivative of e to the t, which is e to the t. What are the units for velocity? Meters per minutes. Just because physicists use meters per second doesn't mean we do. We're mathematicians. Make sure you pay attention. How does it phrase the units? Acceleration. What do we do? Another derivative. What's the derivative of 20t? 20. Derivative of e to the t. E to the t. Derivative of t e to the t. Spoiler alert, same process as before. Derivative of the first, 1 times the second, plus the first times the derivative of the second. Now, if you wanted to, you could combine and say this is 2e to the t, if you wanted to. What are the units? Meters per minute squared. Okay. So, given position, we can find velocity, we can find acceleration, and yeah. So, this is the kind of question that they like. In fact, if you look at the handout and turn it over, you see they love asking word problems about things. Position, what's the velocity, what's the acceleration? When is something at rest? When is the acceleration 0? Things like that. Okay, so we still have some time. We can do a quick economics lesson, or we can jump to the final multiple choice problem. Multiple choice. Okay, well, if we do multiple choice, you got to take some time to think about it. It's about units, so we should be really good at this. All right, the function p of x measures the pounds per square inch. That's PSI. That's what PSI stands for. On the hull of a microsubmersible at a depth of x inches in a particular dense environment. What are the units of p double prime of x? So we have pounds, pounds per inch squared, pounds per inch cubed, pounds per inch to the 4th. The answer is E. Now, why? It's the units of p divided by the units of x squared. Well, what is p? Pounds per square inch. That's pounds per inches squared. Divide by, units of x are inches. So divide by another inches squared. You put them together, you get pounds, inches to the 4th.